This week we are studying earthquakes, what causes earthquakes, and how the energy travels. This is the last new material for the unit test. We'll go through this chapter. Next week we'll continue to talk a little bit about earthquake damage, earthquakes in different places, and volcanoes will be in the second quarter stuff. This is what we learned last week. We went over a very quick flip lesson on this, so I'm just going to zoom through this quickly. But the types of forces. So as the plates are moving, parts of land within the crust experience these different forces. So compression, which is pressing together, tension, which is pulling apart, and shearing, which is side by side. And as you saw in the earthquake video we watched last week, when you have movement along a plate, like the transform boundary of the San Andreas Fault or the one in Haiti, as this shearing, as the fault is moving, it's also causing all sorts of stresses and making other faults along the side. So when we look at what happens to the pieces of the crust, these are some of the different faults. And I know in some ways it's a little confusing, and I have some blocks to kind of show you the example. But basically, the types of faults, if the two parts are pulling away from each other at the fault, you get what's called a normal fault. Now, it's just normal because, I don't know, it's the more common one. It's tension. But basically, the hanging wall slides down, and the foot wall stays in the same place. This is a very minor thing that I would put on a quiz because to me it's a little bit confusing. Strike slip, very straightforward, it's very side by side. In a reverse fault, because it's pushing together, the hanging wall goes up and the foot wall goes down. So, and this is called a reverse fault. This is going upwards and this one's going down. And I will show you with my blocks what's happening here. Okay, so we've just demonstrated all three of these types with the cardboard box earthquake super low-tech demonstrators. So I'll pass those around and you can look at those. And again, one of the things you see in the normal fault, and we see this around here, it almost looks like it's quarried. You'll see this scar along a hillside. Very common. Okay, so questions about this? Yes. So the strike slip, and when you get the boxes, they're just moving side by side. And so this side is here, and this side is here. This is kind of the San Andreas Fault thing, and this one's moving this way, and this one's moving this way. And so sometimes what you'll see, let's move these over here. Oops. That's annoying. So what'll happen is if it started out like this, if there's a river, or maybe you'll see pictures in California where there was like a fence, and then as this moves, yeah, my fence isn't very good. What happens is the fence actually breaks and you can actually see where it's moved and you can actually measure it. And you'll see that if it's a sudden earthquake, you'll see like the roads will be broken and moved offside from each other. If it's just a slow creep, slow tension being released, then you'll get just bending of that. Okay, so again, this is kind of a small part of it. Pass around those earthquake blocks so other people can see them, please. And then the more important, the thing we're going to use in greater detail is this. So first of all, P waves, S waves, and surface waves. So, guys, this is a really important part. We're going to demonstrate this now. This is going to be really important for our activities over the next 2 days. So, first of all, P waves, S waves, and surface waves. So, you'll need to be able to draw these, identify these. The P waves, okay, so seismic, sorry, let's back up a minute. Seismic means shaking. So, seismic waves are shaking waves or energy waves. In general, a wave is how energy is transferring from one place to another. So a water wave, energy is transferring. Sound waves, energy is transferring. Seismic waves, the same thing. So the earthquake, the fault breaks, and that energy gets released. And it's very similar in some ways to dropping a rock in the pond and seeing those waves go out. So the three types. The P waves are also known as the primary waves, P for primary. They travel the fastest. They are the first one that these all get released from the earthquake fault breaking at the same time. The primary waves travel the fastest. So if you are somewhere not standing right on top of the earthquake, these are the ones that arrive first. A primary wave is what's known as a compression wave. In a minute, we'll get our next beautiful earthquake demonstrator, which is a slinky. And so the primary wave, and this is the way sound waves travel first, it's basically compressing it. So if two people are holding the slinky stretched out and you release a chunk of slinky, it makes that compression wave go back and forth. You get to try that in just a minute. Primary waves. Then the secondary wave, secondary, side to side, secondary side to side, and obviously a side to side movement like this, they arrive second. They travel the second fastest. See how confusing those scientists are? Crazy. Then the surface waves are, they arrive third. They are the most destructive. They are the slowest. And the problem is that they're a combination of P wave and S wave type movement. And so it's compressing and stretching and going up and down. And these are the ones where you see we were talking about in extreme earthquakes where actually a roll of earth goes, like a ripple goes through the ground. But it's also motions in two different directions happening at the same time. So these tend to be very destructive to buildings and such. So P waves, S wave, surface waves. These ones you cannot really demonstrate on a slinky because it's kind of two things happening at once. So I'm going to stop the recording for a minute, and you'll get a chance to practice these briefly, and then we'll talk about epicenter and focus and what that has to do with the shaking waves. All right, I think everybody got a chance to do P waves and S waves. And again, those are going to become even more important here in a few minutes. In the past, I've done a longer detailed lab, and I'll probably give you a chance during your lab Thursday, if you have time. But basically, the P waves travel more quickly just because of the way they travel. So let's do a couple other definitions, and then we're going to come back to why P wave, S wave times are important. So write this down. Next words you really need to know are epicenter, focus, and fault. Epicenter, focus, and fault. The epicenter, epi means on top of, center. So epicenter, like an EpiPen, you put on top through the top of your skin, epicenter. The epicenter is the area where the earthquake appears to come from on the surface of the crust. Now, you might be thinking, well, where does it really come from? The focus is actually the place along the fault where the earthquake actually starts, where the friction actually first breaks and the earthquake starts. And when you hear about earthquakes, a lot of times I talk about how deep the earthquakes are. When you think about what a subduction zone looks like with the one plate being pushed under the other, some of those earthquakes are quite deep as opposed to being more shallow. So where earthquake starts. And in the brain pop we watched yesterday, I think they called this the hypocenter, but the textbook calls it the focus. We'll call it the focus. So let's take a quick look at, make a little diagram so that this makes more sense. So where the earthquake appears to come from And the epicenter will be right above the focus. Yes. Right now it's not doing that. Okay. I'll rewrite that in a minute so that it comes out right. So epicenter and focus. So you should definitely draw this picture. Okay. All right, so if we draw a picture like this, here we can just draw some land here, and then we can draw maybe a fault that's going down into the ground like this. This here will be the fault. And then we're going to draw a little city over here. We can do some kind of houses on the outskirts, and then some buildings here, tall buildings, little houses. Okay, and so then here's the fault. Maybe you can even actually see the fault. Okay, so the fault's going to go deep underground. The focus might be a place where the earthquake actually starts, and so these waves are going to start coming out here in all directions and start shaking. The epicenter is going to be directly above that. So it's going to appear that the earthquake starts here. And you can imagine if the fault goes diagonally kind of deep under the earth like this, the fault is going to cause shaking starting here, right? But it might actually be under the city, whereas you don't see the fault at the surface except over here. So the epicenter is going to be right here, and the focus, where the fault actually breaks and starts shaking, is here. And that, of course, is the fault. So that's kind of the general idea of epicenter, fault, and focus. So with the epicenter, that's, the P waves and the S waves are going out in all directions, and we're able to track backwards to find out where that shaking starts. So does everybody have epicenter, fault, and focus? Yeah? Okay. Let's see. That's the earthquake shaking scales. We'll come back to that in just a minute. So with the P waves and the S waves, so the P waves are the fastest, and they travel at a constant speed through the earth. We know how fast P waves travel. The surface waves, sometimes you don't even see the surface waves. They are more destructive. They don't travel as far. But let me show you why we're doing P waves and S waves. S waves, so the S waves also, they're the second fastest. They travel at their own speed, right? That is a known constant speed. So here's why this is useful. If you are right near the earthquake, the P waves and the S waves are going to occur very close together. If you're farther away from the epicenter, they're going to occur farther apart. Now that might seem a little confusing, but this actually makes perfect sense. So let's pick on some people. Who's somebody who's pretty fast running the mile? How fast do you run the mile? Okay, let's just make that 7 because that's easier to remember. So, okay, so if he can run the mile in 7 minutes, and then somebody else here, so they can run the mile in 10 minutes. Okay? That's not a bad time. Now, in a 1 mile race, okay, here's the finish line. in a 1 mile race, what's going to be the difference between this person and this person? 3 minutes. Okay. What about if you what if you ran just like a 100-yard dash? Then what's the time? Is it going to be 3 minutes? No, it's going to be a lot shorter, right? And forget about like sprinting and endurance and that kind of stuff. But if they run in that constant speed, what if they run a 10-mile race? What's going to be the difference between the finish times? 30 minutes, right? Because 3 minutes in 1 mile times 10 miles would be 30 minutes. This is exactly what happens with the P waves and S waves. Okay? So if this is the P wave and this is the S wave, if scientists are measuring those, if the P waves and S waves, and because they are known quantities, because they are known speeds, there's actually a graph, and you can read it right off the graph. You read it off the graph, and the graph says, if there's 2 minutes between the arrival of the P wave and the S wave, then the epicenter is this far away. Does that kind of make sense? So that's the activity we're going to do tomorrow, is looking at that. But this is what it amounts to. If they always travel at the same speed, you know. You know if these two people ran at that constant speed for the whole race and finished 30 minutes apart, you know that the race was 10 miles long. Yes? Yes. Yes. Actually, thank you. That's a really good example. Okay, so lightning and thunder, light travels very fast, almost instantaneous to reach your eye, but the speed of sound is much slower. So if you know how slow the sound travels, and you can estimate it, then when you see lightning, you count how long until you hear thunder, you know how far away the storm is. That is exactly the same idea. And so with this, we can actually predict, we can actually calculate where the earthquake started. Why does that matter? Well, it helps us map the faults underground. It helps us identify danger areas. And one of the most awesome things about this, what if you're relatively far away and you feel the P wave? The P wave is the least destructive. So if they could send out a warning when that P wave is detected, people farther away might have up to a couple minutes to get to safety. Is a couple minutes enough time? Yeah, it might be, because this isn't an earthquake warning. This would be an earthquake just happened. The S waves are coming. That means, you know, get to safety, get under the table, get out of the elevators, get out of the parking garage, whatever. And in fact, at the very beginning of the school year, there was an earthquake. They're actually using this technology. It's at the end of the video we started watching. In California, they're using this technology. And an alert will go out over people's cell phones and say, P waves were just detected in this area. There is an earthquake that has occurred. Get to safety. And it actually did work at this last earthquake. Because if you just warn people, they're like, yeah, it might happen, it might not. But when you can tell them, right now an earthquake happened, get to safety, it can actually make a difference. Okay, couple quick questions, and then we'll talk about the earthquake measuring waves. All right, the last new piece about earthquakes that you need to know is this. There are 3 different types of earthquake measuring scales, okay? So these 3 are very different from each other, and they measure different things. Let's just kind of work through this in a non-sequential order. The Richter scale is the one people are most familiar with. The Richter scale actually measures shaking. And you cannot rate something on the Richter scale unless you have a seismograph, you know, which is one of those little things, and this wiggles back and forth and makes one of those long tapes that looks like this, right? That's a seismograph. And I have these little sample, you know, earthquake seismographs to measure shaking that you can. So these measure the shaking energy. They're pretty reliable. They're very useful. The only bad thing is If there's no seismographs, you can't really measure the earthquake. 1 through 10, and each one, so like a 2 on the Richter scale, is 10 times more powerful than the 1. Okay? What's that? That's for the amount of energy. Okay? But for the shaking, the amount of shaking. And, you know, a 1 or a 2, honestly, when a train goes by, if you're sitting nearby, that would measure a 1 or a 2. The very, like 6 and greater are some significant earthquakes. Okay, then moment magnitude, which is what I think you were getting at there, is actually, you can't do the moment magnitude until after the earthquake has already happened, and then they look at all the data and they say how much energy was released. And it's a very similar scale to the Richter scale, and in fact, when they say that was a 7, magnitude 7 earthquake, usually it's kind of, it's got some elements of both of this. But that one, and they were talking about this on the video too, it actually moves up by 30. It's a logarithmic thing. But if you think about, if this is a 1, if you're making the wave, and then this is 3 bricks, the area under the curve doesn't just go up in a linear manner. So anyways, the Richter scale, moment magnitude scale. And then the one I find really fascinating is the modified Mercalli scale. You know it'll be modified Mercalli because they're using Roman numerals. And this one is very interesting to me because this one, after the fact, they go back and they look at the damage done. And so it doesn't require any instruments. You don't need any seismographs. You don't need anything like that. You don't need satellite pictures or anything. You just look at what damage happened to what types of buildings, and they use that for the modified Mercalli. And let me see if I have. So on the modified Mercalli, a 1 or a 2 is just going to be slight vibrations. If you were outdoors, you didn't even know it happened. You know, 2, 3, 4. And then when you get up to like 5, then it talks about the type of masonry. Like a well-built building would vibrate a little bit. A 5 like knocks dishes off the walls. And when you get up to the 10, 11, and 12 in this is when people actually see the ground move. The ground splits and opens up. General panic, people freak out and run around and scream. As opposed to a 1 where if you're outdoors, you don't even know it happened. And so this is really useful because we can look back at historical accounts of earthquakes and look at them and talk about how damaging they may have been. Because if there's nothing, no monitors there to measure it, it's difficult to do this. But you can always look back and look at this. Okay, couple questions. Yes.